Okay, so the framework is the following. So X is a Hadamard manifold, Hadamard space. So it's simply connected, contractible, homomorphic to Rn, Riemann manifold with curvature between 0 and -1, and sometimes we assume that curvature is simply negative, and sometimes we assume that it's not, but then we assume that X is analytic. G is the group of isometries of X, and gamma is a subgroup of G. And gamma is a discrete subgroup, and M is a Hadamard manifold, is a X manifold, X mod gamma. We call it X manifold, and or X orbifold in general. The difference is whether gamma acts freely or not, which is equivalent to whether gamma is a torsion element or not. So in most cases we assume that it's a manifold because then it's easier to deal with. And somehow we want to control the topological complexity of M in terms of this parameter, the volume of M. So we want to understand how volume M controls the complexity, topological complexity of M. So what I want to do today is the following. So I want to show, so then we defined, there was epsilon, which is called the Margulis constant. So let me recall what it means. So there is a classical lemma of Margulis, called the Margulis lemma, that there is such an epsilon, depend on the dimension. This is the dimension which is strictly positive, such that independently of gamma, for X, in X, the group generated by all gamma in gamma, such that the displacement of X is less than epsilon, where d gamma of X is the displacement function, is virtually nilpotent. So it has an important subgroup of finite index, and in fact you can also bound the index. There is the M, which also depend on the dimension, such that which bound the index. I don't think we'll need it today. So this is the Margulis constant, and then there is the fixed in decomposition. M less than epsilon is a set of all X in M such that the injectivity radius in M of X is less than epsilon, and M greater than epsilon is M minus. That's the epsilon thick part and the epsilon thin part, and and the idea of is to do it by two steps. Is first to relate the topology of M to the topology of the thick part, somehow to control the complexity that is contributed by the thin part, and we can do that to some extent, not in complete generality. And the second step is to control the topology of the thick part. So that's the two things that. Let me recall that the thin part, tilde, when I look at when I take a subset here and I do tilde, I mean its preimage in X. So the preimage in X, in the Hadamard space of the thin part, is the union over all gamma in gamma minus the identity element of the sublevel set D gamma less than 2 epsilon. So let's assume that Margulis constant is satisfied. So, and this is a union of these are convex set with smooth boundary.
What is D gamma here?
D gamma is the displacement function.
Oh.
So D gamma, because of the non-positive curvature, the distance between any two geodesic is a convex function. So the T goes to the distance between C1 of T to C2 of T is a convex function. That's actually, this is equivalent, if you want, to non-positive curvature. It's convex. And this implies that the displacement function is a convex function. So if you restrict it to a geodesic, it's a convex function from R to R. And therefore sublevel sets are convex sets. So these are convex sets with manually, so somehow you imagine it to be a union of convex set D gamma 1 less than epsilon and so on. So that's the thick part, that's the thin part. And so these sets are somehow controllable in some sense, but we need also a control on the angles here somehow. If you want to, okay, for later use we will need something like that. I don't know if we get there today. But what I do want to do today is the following. So we discussed. We started to discuss properties of isometries, of individual isometries, and then of a group of isometries. And the motivation is to prove the following. So again, let gamma be as before, and let actually, let me give some definition. So in fact, let M be the index in Margulis net. So before I say that I will not need it, but I think I will need it. So there is some M depending on the dimension, and let's say that for let's say gamma in the isometry group of X, gamma is let's say M stable. This is definition. If the minimal set, minimum gamma equals minimum gamma to the I for all I from 1 to n. So what is the minimal set? This is by definition, this is a set where the displacement attains the minimum. So it could be empty if gamma is parabolic element. So this set is empty. But if it's a semi-simple element, then the set is not empty. And the set where the gamma attains the minimum is a set of all the excess of gamma. So gamma has many excess parallel, and it translates on them and then do something outside. So we saw that this is of the form W cross R, and gamma fix pointwise W and act by translation on R, and this is a convex subset of the full space X, and gamma do some rotation around this subspace. So any semi-simple element has such a subset where the minimal, when the minimum of the displacement is attained. Parabolic element, this is empty set. Fixed point at infinity in the boundary, but not on the space. But semi-simple element is this. And the translation is 0 if and only if it's elliptic, if and only if there is a fixed point. But in the case we consider manifold, it's semi-simple is hyperbolic, so the displacement here is not 0. A priori, the minimal set of gamma to the I contains the minimal set of gamma. If gamma acts on by translation somewhere, then any power of it acts by translation. But maybe there could be more points. Maybe there is some rotation that if you apply, if you take gamma to the 5, some rotation becomes trivial, so there will be more excess. So a priori, or even for fixed points, you can imagine in R2 rotation by 90 degrees, it has only one fixed point. But if you take its fourth power, then it fixes everything. So the set of fixed points can increase when you take power. But we say that gamma is stable, is M stable if it does not increase for small power. And here there is a lemma.
So M changes for each lemma?
No, M is the constant from the Margulis lemma. M is a constant, so Margulis lemma says that that if I look at the point X and a discrete group gamma, and I look at the element in gamma that displaces X by less than 2 epsilon, then it has an idempotent subgroup of index at most M. And this M is depend only on the dimension. And that's the constant of Margulis. Same constant appear in Bieberbach theorem, in about crystallographic manifolds, and you are virtually nilpotent, and this bound of and here is a simple lemma. Maybe I'll leave it as an exercise unless you ask. There exists M depending on M such that for any gamma in the isometry group of X, gamma to the M, or gamma to, there exists K, which is at most M, such that if I replace gamma by gamma to the K, is M stable. And it can replace any isometry by some small power, which become M stable. Let me tell you what is the reason for that, and then if you want, I can give a rigorous proof, but maybe I'll leave it as an exercise after giving you the reasons.
Small.
What?
Small M.
No. There is K, which is smaller than big capital M, such that gamma to the K is at most is M stable. M you should think about it as 100, and capital M as 100 factorial or something. But there is some bound. And the reason is the following. So the minimal set is a submanifold. It is a totally geodesic submanifold. So it has a dimension. So it can increase, but only finitely many steps. So I can look at the first M powers of my element. If the minimal set does not increase, then my element is already stable. If it increases, then look at this power, and then look at its first m power. If it does not increase, then this was stable. If it increases, then I replace it again. I can do it only finitely many times because the dimension is bound. So this is somehow the proof of this exercise. Okay, so this I leave it to you to Okay, now let me formulate what I want to do. The idea, you have this manifold, which it has thin part and it has thick part. Let's think of this as a thin part. This is a thin part. And the idea that I want to show that there is a deformation retract to the thick part. At any point I can move toward the thick part. But I cannot do it in general because if I'm in some point, I will look in which direction the injectivity radius is increasing. So in some points I will have a problem. If I have a short geodesic, at least intuitively it is clear that here I need to go to the right, here I need to go to the left, but here I don't know where to go to this side. So so the idea is what we want to show that we want to show that there is some submanifold. Here this is geodesic, or a union of submanifold. Maybe there will be several of them and they will intersect each other, such that if I throw them from my space, then there is a deformation retract from what's left to the thick. So okay.
So in higher dimension, it can still be connected, right?
So if what I throw it's of codimension 1, it will not be connected. But if it's of codimension 2, then it's already connected.
And what is it going to do?
And if it's of codimension bigger than 2, then I will not even change the fundamental group.
Yeah.
And okay, we will try to control it later. But yes, it will be of codimension 1 only in dimension 2.
Oh.
So it will be connected. And it will be connected, and actually in most cases it will be of higher codimension, so it won't change the fundamental group, so we're in a good shape. But this we will do later. So okay. So now I want to define this submanifold. So definition. The stable singular manifold. The M epsilon stable singular set is defined as follow. So n tilde will be okay. Maybe before the definition, I told you that every element I can raise to a small power. Which makes it stable. So lemma. Oh, not lemma. Definition. Gamma star is gamma to the I, where I in n is the minimum, such that gamma to the I is m stable. I take the smallest power, which makes it m stable. And you know that I is at most m. Okay, the lemma and now. I will define n to be the union of minimum gamma such that still not clear to me how to define n precisely. I want to do it, so n will be the union of the minimal set of some elements, but what will be these elements that I'm considering? I don't know if stable is what I want. Actually, okay, let's go with stable. I think it will work. So the minimum of all gamma such that let's say d gamma is less than f.
Gamma star?
No, minimum of all gamma such that gamma is stable, m stable, and the infimum of d gamma, we had some notation for it, no? The norm, or how do we call it, rho of gamma, which is less than x. So rho of gamma was the norm, or the spectral norm, or spectral radius, or whatever. Rho of gamma was the infimum of the displacement. Okay, so I throw out minimal sets of m stable elements where the displacement is less than epsilon. So it's a locally finite union because gamma is discrete and the action is proper, G acts properly, and the stabilizer of each point is compact. So this will be n tilde, and n inside m will be the projection. N is the projection to m of n tilde. If you want n tilde divided by gamma. So n tilde is a gamma invariant set. Okay, so this is the, and what I would like to prove is that there is deformation retract from gamma minus n. So maybe I will make changes on the way because the goal is something that I don't know to do in full detail. So everything I know to do many things for symmetric spaces or for manifold of negative curvature, but I don't know to do it in general. But I think it's only of how you formulate things precisely, it should work out. So that's, there may be some changes along the way, but what we would like to prove is the following proposition. And this is all in the spirit of Bauman, Gomer, Schroeder, and main ideas are from there, but we aim on goals that are not there. So the proposition is that there is a deformation retract from m minus n to m to this. This will be I didn't prove it, but it will follow. We will see that it's a manifold with boundary, and there is a deformation retract from here to there.
Wait, topologically it's manifold with boundaries.
It's a what? The thick part is a manifold with boundary.
Topologically, not smooth.
No, not smooth. No, it's not. It's, you can make it a manifold with corner.
Something. What was the definition you had at the bottom?
Which definition?
You said that we're going to go back to this definition and this definition before. Did you erase it?
I don't.
You hold it.
The n.
Is that? Oh, okay.
The stable.
Oh.
Okay.
Then. That's an.
N tilde.
Oh, that's in it.
Yeah,
Okay.
that is it.
And for this proposition, there's no restriction on the
Okay.
dimension.
Thank you.
Sorry?
There's no restriction on the dimension.
Dimension is fixed.
But it's okay also in dimension 2, even if
Yeah, in dimension 2.
even
Yeah.
if the thin part's not connected.
In dimension 2, the thick part is not connected, but yeah, it's not. It doesn't. Actually, in dimension 2, we know everything. Everything follows from Gauss connected.
But M without N is not connected and
M minus N is usually it will be connected in higher dimension. It will be actually N will be of small codimension, of large codimension. So N will be the dimension of. For instance, if it's strictly negative curvature, then N is one dimensional. So if M is 10-dimensional, then this is of codimension 9. So almost all the topological information is left when you throw out something of small dimension. But in general, it is more complicated. For instance, if M is the locally symmetric space with the group for isometry of the symmetric space is SL3R, then a priori N could be, so it's 5-dimensional space, and a priori N could be 3-dimensional. So this is somehow a case which is complicated. So okay, maybe I'll give examples later. So how do we do that? So how do we find this deformation retract?
N is always flat.
N is not necessarily flat. So N, no. So actually, let's give an example. So let's give an example. Suppose that G is SL3R, 3x3 matrices with determinant 1, and this acts on the symmetric space X, which is P1. This is the symmetric space of all. You think about it. Of one model of it is all the positive definite 3x3 matrices, symmetric matrices of determinant 1. So and positive definite. So if you want, or the space of all ellipsoids in R3, or the space of all Euclidean norm on R3, or the space of all 3x3 positive definite matrices of determinant.
What's X in this case?
What?
What's X in this case?
X is the symmetric space of SL3R. The shortest way is to write it by SL3R modulo SO3, but this says nothing about the Riemannian metric. But the Riemannian metric is defined on the tangent space of the identity by the standard Hilbert-Schmidt norm. So the trace of A B transpose is the inner product, or A. Okay, I don't want to describe this example in details now because it will take me 2 hours. So I just assume you know it, even though most of you probably don't know it.
And someone should do it in the Midrash.
What?
Someone should do it in the Midrash.
Yeah, someone should describe it in the Midrash. Okay. We discuss rank 1 symmetric space negative curvature, or will discuss, but this is the higher rank of example. And here, if you take gamma to be the isometry which acts, let's say, by 2 to 1/4. By the way, so this cannot be a lattice because of arithmeticity, but never mind, forget it. So assume that we have, assume that we have some isometry of the form alpha, lambda minus 2. So this is an isometry. So it's an hyperbolic isometry. So suppose lambda is a real number bigger than 1, and so it is a hyperbolic isometry. It has an axis on this 5-dimensional space. This space is 5-dimensional because SL3 is 8-dimensional and SO3 is 3-dimensional. So this is 5-dimensional space, and this isometry acts with axes, but it has many axes. Actually, if you conjugate this, or if you if you think about it, the centralizer of this element is GL2. Is anything of the form this commute with that. So it's a GL2, and if you take an element in the axis and move it by something from the centralizer, you get to another axis of this element. So it means that the set of all axes is exactly the symmetric space of this GL2, which will be H2 hyperbolic plane cross R. Okay, I don't want to go into details here, but there will be a three-dimensional space, which is hyperbolic space times R. And this element will act by translation on this R and fix point-wise this H. But it's not flat. It's that's the idea. So it's a lot of parallel geodesics, but they don't form in general they don't form Euclidean plane space. But in many cases they do. In many cases they do. This is some of special examples. So in many cases it doesn't. Okay, let's go on a bit and we want to prove this proposition or theorem, if actually it is. And this theorem should be attributed to Van Gogh Schroeder, although I didn't say it precisely as they do it because I need some. Okay, basically it is there, but I don't know exactly if I need this or some variation of that, and this will follow from the following fact. So now let's go back to isometry. And the lemma that I want to prove is the following. So let gamma gamma was the group before. So let's delta be virtually important group of isometries. Delta is a subgroup of isometries of X. And suppose the delta is generated by gamma 1 up to gamma n, is generated by finitely many elements. And so this is the case that we need to deal, and then let X be a set inside X, a point inside X. Then I claim the following, and there is a tangent vector, there is n in the tangent space, such that the gradient of d gamma I in this direction is non-zero for all I, for I1. So and it's strictly positive if X is not in gamma I, in the minimal set of gamma I star. Okay, so if you're on the short geodesic on the axis of gamma I, then I don't know to find such a direction. You cannot actually. In general, you cannot. But if you're not there, if you're not on the middle, if you're not on this short geodesic, you're not in then this direction is independent of gamma I, and it somehow increase the displacement of every generator. This is somehow will give you a clue how to do the deformation of time.
Should the second line be less?
Sorry?
Should the second line be less than? Or something? You have greater than.
Greater than.
It means it's
Strictly positive.
Strictly positive.
Here it's no negative, and here it's strictly positive. So that's the lemma. And with this lemma we can do the deformation retract. By the way, one thing that you can deduce from this lemma is that actually the thick part is a manifold with boundary. I think it's because you remember I told you that I don't want to go into the proof of the lemma before the break, and because the proof of the lemma will take maybe 15 minutes, and also the proof of the deformation to explain the deformation retract will take more. So, but I want to take a break in a few minutes. But before that, let me just tell you that it tells you that if you have a virtually potent group of isometries, then you can find a direction which somehow is transversal to the level set of the displacement function. So it's increased it's increased all of them. It's increased the displacement function. And the thick part, or the thin part, if you remember, it was a union of convex sets, but this convex set were sub-level set of displacement function. So now, suppose I'm here on the boundary of the thin part. So I know that there is a transversal direction that increase or decrease and together with this information you can show that locally this is a manifold with boundary, and therefore globally it's a manifold with boundary. So that's, without going to details, I just say that from this lemma you can deduce, if you want, I don't know if we will use it. I'm not sure we will use it at any point, but if we do, then from this lemma we can deduce that the thick part is a manifold with boundary. So far we just need it's just a compact set, the thick part, but and maybe it will be enough, I don't know. But sometimes if you want to use Poincare duality or so you need to know it's a manifold with boundary. So this will follow from that. But from that also we follow the deformation retract. So let's have a break, and then I'll explain how to prove the lemma and also how to deduce the deformation retract. Modulo, okay, maybe not in full detail. Maybe, okay, we'll see. טוב, הזדמנות להמשיך. פתאום הבנתי